Hello, math students. Today's video is going to focus a little bit more on graph sketching with limits. We actually started this in our last video where we focused on the different types of discontinuities a rational function can have. So we're going to continue on piggybacking off of those notes and just adding a couple more steps at the end to sketch a complete graph. So here's the example we're working on in today's video. It says, consider the rational function f of x equals x squared plus 7x minus 8 all over x squared minus 5x plus 4. So as I said in the last video, if you asked me to just throw down a sketch of this graph, that would be kind of difficult for me to do just off the top of my head because it's not as simple as a linear function or a quadratic function might be. So I need to go through more of a process to find some key points on this graph to help me construct it. So I'm going to guide you through here with these steps, and hopefully by the end of this we're going to have a nice graph. Okay, so number one says find the values of x where the discontinuities on the graph occur. So we've already studied discontinuities, and we know that to find them we set the denominator of the rational function equal to 0 and we solve for x. These will be the values of x that make the denominator 0, which make the function undefined. So this looks like it's going to factor for me. So I'm going to factor this quadratic into x minus 4 times x minus 1. I'm going to set both quantities equal to 0 and then just solve those for x. So I'm going to get x equals 4 or x equals 1. Okay, so put that on the answer line, x equals 4 or x equals 1. Great. Okay, number two, determine if these discontinuities, there's that word again, are wholes or vertical asymptotes. So again, we addressed this in our last video. So I'm going to plug x equals 4 into my function, f of 4, and I'm also going to plug 1 in, f of 1, and I know that those values of x make the denominator 0, so I can just put the zeros on the bottom right away. I will have to plug into my numerator, so for f of 4, if I look up at the numerator, I'm going to have 4 squared plus 7 times 4 minus 8. And then for f of 1, I'm going to have 1 squared plus 7 times 1 minus 8. And that is going to result on the top here. We have 16 plus 28 minus 8. That looks like it's going to be 36 over 0. And here with f of 1, we're going to have 8 minus 8, 0 over 0. So this indicates for this one that we have a vertical asymptote when x equals 4, and we have a whole when x is 1. So there are my answers. I'll push that with an arrow toward the answer line so I don't have to recopy it. Okay, number 3. If there is a whole, which we have, determine the coordinates. And if not, just write not applicable. Okay, so we do have a whole. So again, from our last video, we know that to find the coordinates of the whole, we know that x is 1, that we're approaching a whole when x is 1, but we have to find what the y value is approaching. Even though we're undefined right at 1, we can still have a limit as x approaches 1, which will place that discontinuity. So I'm going to do the limit as x approaches 1 of my function x squared plus 7x minus 8 divided by x squared minus 5x plus 4. And I know when I plug that in, I get 0 over 0 because I actually did that up top here. So now using some of my factoring techniques, or I'm sorry, my limit solving techniques, I'm going to factor this and see if anything cancels out. So on the top, I'm going to factor into x plus 8, x minus 1, and on the bottom, x minus 4, x minus 1. And so the x minus 1s will cancel out. And when I plug 1 back into my reduced function, I get 1 plus 8 divided by 1 minus 4. So that's 9 divided by negative 3, which is negative 3. So that comes out really nicely. So I'm going to drag this y value over here. So my hole is located at 1, negative 3. Okay, number 4. For each vertical asymptote, evaluate the limits left and right of it. Okay, so we do have a vertical asymptote. It occurs when x is 4. So I need to look at the limit as x approaches 4 from the left, as well as the limit as x approaches 4 from the right. And I'm going to use the reduced function from step 3. I'm going to use x plus 8 divided by x minus 4. Again, this was gone over why we can do that in the last video. You can also use the original function. It's just going to be a little bit more involved when you plug 4 from the right and 4 from the left in. The reduced function is much nicer. Okay, so 4 from the left, I might plug something like 3.9 in. So if I have 3.9 plus 8 divided by 3.9 minus 4, it's going to give me 11.9 over negative 0.1. And again, in the last video, we extensively went into why a number very close here to 12 divided by a number very close to 0 but negative travels toward negative infinity. When we plug 4 from the right, we have 4.1 plus 8 divided by 4.1 minus 4. And that's going to be 12.1 divided by positive 0.1. And again, we talked about the reason that heads toward positive infinity. Okay, so that completes the first side of the sheet. So we're going to flip it over. This is an add-on. Now this is where your last homework assignment stopped. We're going to actually continue on and do number 5 to find more graphical information. It says find the horizontal asymptotes. The final answer to this question should be in the form of an equation for a horizontal line. So I know that my answer is going to be y equals some number. Now that number is going to be my horizontal asymptote. If I get a real number here, if I end up getting an answer of infinity or negative infinity, then we know we do not have a horizontal asymptote. So to find horizontal asymptotes, I must set up the limit as x approaches positive infinity, as well as the limit as x approaches negative infinity. Now, of what function? Well, you can either use the original here, or